Yes, welcome back again. My name is Johannes. So let's continue to pumping head. So this is an arrangement. We have reservoir and piping system along with the pump. So we are given water at 15 degrees centigrade is to be discharged from a reservoir at a rate of 18 liters per second using two horizontal cast iron pipes connected to series and a pump between them. So the first pipe is 20 meters long, which is this is the first pipe, and has a diameter of 6 centimeters, while the second pipe is 35 meters and has 3 centimeter diameter. So the water level in the reservoir is 30 meter above the center line of this pipe. And also the pipe entrance is sharp-edged and losses associated with the connection of the pump are negligible, neglecting the effect of the kinetic energy correction factor, determine the required pumping head and the minimum pumping power to maintain the indicated flow rate. So we have 6 centimeter diameter, then it will reduce to 3 centimeter diameter. So we have discharge already given. So we have two cast iron pipes. So I think we have friction factor for this cast iron. So we will use. So let me give you highlight on this one. Let me give you highlight. So according to Bernoulli's equation, we have this equation, total energy just in point 1, which is this one, point 1, and total energy at this point will be equal. So P1 over gamma plus B1 square over 2G plus Z1 plus manometric head available for this pumping, P2 over gamma plus P2 square over 2G plus Z2 plus HF1. So from 1 up to 2 points, what are the losses indicated? So I think we have this equation. So we have total loss. Total loss is the sum of minor and major. So we have two losses are just incorporated in this piping system along with the reservoir. So we have major loss and also minor loss. So major loss is due to pipe friction. We have here major loss for the first 20 meter. We have major loss for the second 35 meter. We have again loss. So we have the same pipe, which is cast iron we will use. So please check F for cast iron from table. You can find F, friction factor for cast iron. So I think we have this one, which is according to Darcy-Weisbach equation, summation of Fi Li Vi square over Di 2G. So we need to compute the velocity in 6 centimeter diameter and 3 centimeter diameter. First, we have to compute total loss. So just according to continuity equation, if you have Q here, you have Q. Q is already given. So once Q is given, you can just apply area times velocity. Then you can find the velocity, which is important, area times velocity. Area times velocity. So this is just important issue. We have total loss which is major plus minor. So minor loss which is due to entrance and fitting, etc. But here, just the losses associated with the connection of the pump are negligible. So we have only one loss, which is entrance loss. At this point, we have K. So this K will be just entrance loss 0.5 from table. K again 0.5 for sharp-edged entry. So we have sharp-edged entry. Then you have major loss in the first pipe, in the second pipe again. So you sum up here, then we have only one K1 which is entrance loss. Then find V, which is V1. At this point, you can find from continuity equation and Bernoulli's equation, you can have this equation. Then finally, we will have Z2 minus Z1 again. We have 30 meter. Then just by substitution, you can just find the pumping head, which is the manometric head, but find the velocity according to this equation. So let me continue. Pump pressure. Pump pressure. The diagram shows a pump delivering water through a pipe 30 mm bore to a tank, which is this is the tank and this is the pump. Find the pressure at point 1. What will be the pressure reading at point 1 when the flow rate is 1.4 decimeter cube per second? The density of water is given 1000 and the loss of pressure due to friction is 50 kilopascal. So you will have point 1 and point 2, then you can just apply. Now let's see the solution. So area of the bore, which is total area, which is net area, pi over 4 d square. So we have this area, then flow rate, which is given 1.4 decimeter cube per second, then we have this one, 0.014, which is dc is in the power of minus 2, then just 1.4 you have negative 3. So you go this one in meter cube per second, then mean velocity, which is very important according to quantity equation, q over area, we have 1.98 meter per second. This is the velocity of the pipe. So applying Bernoulli's equation between point 1 and the tank. Point 1 and the tank. Let me go back one step. This is point 1. At this point and at this point, you can apply Bernoulli's equation. So Bernoulli's equation will be P1, just you multiply the original equation by rho g to both sides. So you will get pressure P1 plus rho g Z1 plus rho g will be cancelled, rho V1 square over 2 equal to P2 rho g Z2 plus rho U2 square over 2 plus pressure loss. So the pressure loss is given, so we substitute. Now pressure loss is 50 kilopascal or 50,000 pascal. So the velocity at point 1 is already 1.98 from the above, and at the surface is 0. The surface will be 0. So P1 plus, just at the surface you have 0, which is the datum 0 d to Z1. Then you simply substitute density times velocity square over 2, then equal to P2, which is 0, which is at second pressure of the surface 0. So you substitute 0 here, then rho g, Z2, you have Z2 elevation. Then finally, you can find this, which is this one. This is G times Z. Then you have 50 kilopascal, 50,000. Then this is the gauge pressure. The gauge pressure at point 1. Okay. Other example is, let's go to specific speed and rotational speed. So specific speed of pump will be computed now. So it is desired to deliver 100 liters per second under a head of 270 meters with a single stage pump. What would be the minimum rotative speed that could be used? Assuming that the minimum practical specific speed is 10. This is the minimum practical specific speed. And the second problem is, for the conditions of A, how many stages must the pump, which is with NS 10, have a rotative speed of 600 revolution per minute to be used? So for this revolution per minute to be used, how many stages? Let's see the solution. So specific speed of pump is given by this equation, which is this one, which is rotational speed, square root of Q divided by the head, the power of 3 over 4. So you can find this rotational speed. Rotational speed will be computed because we have specific speed given, then rearranging the equation, just crisscrossing, then we have rotational speed, which is 2106 revolution per minute for the first problem. But for the second, for the conditions of A, how many stages must the pump with NS 10, which we have, just how many stages must the pump have if a rotative speed of 600 RPM is to be used? So using 600 RPM, you will compute again. So we have 0.1 meter cube per second flow rate with 10, 19 we have. So just 50.6 per stage. We have 50.6 per stage will be just the head. So this would mean total required stages we have 270, which is the head available. Then you have to divide 270 divided by 50. So if you divide 5.34 or 6 stages are required. 6 stages are required. So single stage we have. So you compute this one 50.6 per stage for each stage. For each stage we have 50.6. Then for the total we need 5 or 5.34 stages or 6 approximately. Okay, the other example is head. Head and power developed by a pump. So water is being pumped from a lower reservoir. This is a lower reservoir to a higher elevation, which is 100-meter elevation to upper elevation at this one. So from lower elevation at elevation of 100 to a higher elevation of 150. So this is higher elevation, this is lower elevation. So with a flow rate of 2 meter cube per second. And the pipe has a length of 900 meter. This is the pipe length, total length of the pipe, rising main pipe, and the diameter 60 centimeter. So if the efficiency of the pump is 75%, if the efficiency of the pump is 75%, what is the shaft power required to drive the pump? So to drive the pump, what would be the shaft power? Take C, which is new welded steel pipe material, according to Hazen-Williams equation, C 120. Take 120, then what is the shaft power required to drive the pump? So this is the arrangement, reservoir and pipe and pump system. And the second problem is what is the cost of electric energy to fill a reservoir of 8,000 meter cube if the motor efficiency is 90%. So take cost of energy 15.45 cents per kilowatt hour, just as according to US. So let's see solution. So we have answer just for the first shaft power should be this one, and cost of energy will be this one. Let us see solution. So first, given parameter, we have to identify Q 2 meter cube per second, Z1, which is this one. At this point, we have 100 meter, and at the second point, at this one point, which is 150 meter. So diameter of the pipe, the same diameter we are going to use, 0.6 meter, and the length of the pipe is 900 meter, and C is given, just new welded steel pipe material, which is 120. Pump efficiency is given, and motor efficiency is given. So here, pump and motor arrangement, I will show you later on. So let's go to the solution now. The first solution is assuming the velocities are initially at rest. The velocities are initially at rest, and comparing to the reservoir diameter. So this would mean V1 approximately 0, V2 approximately 0, and P1, which is open to the atmosphere, which is 0, and P2 again 0, both open to the atmosphere. Then, according to just applying Bernoulli's equation between point 1 and point 2, both reservoirs, which is this one, this is point 1, this is point 2, this is point 2. So we have Bernoulli's equation, point 1 and point 2. Now, let us calculate. So the same pressure head plus velocity head plus potential head plus manometric head equal to the second, but you have to add the loss equal. So just P1 0, P1 0, then cancel 0, then you have this equation. This is 100 meter, which is the difference between this one So 100 meter is the lower elevation, which is Z1, and 150 is the upper reservoir elevation. So remain HF, which is the loss. This is equation 1. Then according to Hazen-Williams equation, the head loss is given by this equation. This is according to Hazen-Williams equation because new welded steel material is given and it is 120, so you have to use this equation. So we get this is the head loss between 0.1 and 0.2. So you substitute this in the above equation, in this equation, to get manometric head. So substituting in equation 1, so you have 150 plus 59.301, which is HF. Then you subtract 100. Then you get, this is the manometric head. The manometric head available. So the efficiency of the pump is given by this equation. Efficiency of the pump is output power, which is hydraulic power, divided by input power, shaft power required to drive the pump. Then hydraulic power is just rho g QH manometric divided by input power. So input power. So this is a general equation. You have to keep in mind this equation. Then let's see solution now. The shaft power is given by now, just after rearranging, the just power input will be rho g QH. This is the manometric head. Then this is pump efficiency already given. Then we get this 2859.314 times 10 to the power of 3 watt. So to convert into kilowatt, 2859.314 kilowatt. So, and the brake horsepower is given by power input divided by 75. This is conversion factor. So the brake horsepower is this one, 38.1812 horsepower. To find the cost of electric energy, first we have to find the electric energy or the electrical power supplied to the motor so that the pump runs. Let us see the installation arrangement as follows. So you have motor here, then motor is connected with a pump. So you just supply power, which is electrical power is supplied to the motor. So this motor is coupled with the pump by shaft. So you have input power. So the input power from just coming here from motor will be just generating here the pump power input. Then you have output power, which is hydraulic power, rho g QH. So this is the output power. So according to this arrangement, now let me show you here. So this is a good picture of pump components. We have here electric supply, here electric supply. We have electric supply nodes. Then once you just power connection, then if you just open from switch here, then this is just the electric motor, which is just to drive the shaft. Then here it will run the shaft. So you have coupling guard here. Then you have casing here. Then once it will rotate, then this is just the power, which is the input power. So once electric power is connected here, then here you have input power will be going to this pump. So the pump is with the casing and discharge nozzle and suction nozzle you have. Then this is just the suction nozzle. Water will come through this. Here, through this. Then after rotating, it will take water. Then it will go to this direction. This is the discharge out, discharge nozzle. So this is the arrangement from the above. You can just understand. Then finally, you have like this. So just you have here electric is connected or generator is connected with this motor. Then this motor is shaft is connected here. Then it will take water. Then it will go to this direction. So this is the discharge nozzle. So you have hose. Then it will go from the source. Then finally, you can just adjust. So I think this is also very important. You have motor, electric motor, shaft is connected to the pump. So impeller is here. You have then it will take water. So water is taking through this suction pipe, then it will go to this one, discharge nozzle. So you have just here, you have a shaft in nozzle, then it will just rotate. So this shaft, so electric motor. So according to the previous arrangement, first you have to have power supplied to this electric motor. Then this power electric motor will be just connected by shaft. It will have power input to this motor. So this power input will take water from the source. Then it will take out water to this direction, which is output power or hydraulic power, which is rho G QH manometric head. So this is a manometric head available. So I think you have now, let us see the solution. So the overall efficiency of the system is given by this equation. So this is the overall efficiency, water plus times pump efficiency, which is power output divided by input power. So hydraulic power over power supplied to the motor. This is power supplied to the motor, which is the input power. So you have rho G QH manometric over electrical power. So once we have this, now we can compute the power supplied to the motor, which is electrical power, just crisscross. So take this one, electrical power, rho G QH manometric head, you multiply. So this is the output power, which is just taking out, and then this is, you have to multiply motor efficiency and pump efficiency, then you get this result. So this is 3177.015 kilowatt, which is the electrical power supplied to the motor. Then to find just cost of electric energy, time taken. You have to find time taken to fill the reservoir volume, 8,000 meter cube. So from Q, V over T, volume over T, you can just crisscross this one, find T. T is time of pumping, 8,000 meter cube divided by flow rate, which is 2 meter cube per second. You get 4,000 seconds. It requires 4,000 seconds. Then time of pumping is 1.11 hours. Now you can find energy now. Energy is power times time. Then power is already computed. This one, power is this one. Then you multiply by this time of pumping. So if you have this time of pumping, if you vary, then the energy also will vary. So this will be 3,526.487 kilowatt hour. So this is the energy. So energy cost is cost rate multiplied by energy. The cost rate is already given, 15.45 cents per kilowatt hour. You multiply by energy, then you get 54,484.22 cents or 544.84 USD. So this is the result. So I think thank you very much for watching this video. If you have any question or doubt regarding this tutorial problems, please forward through comment suggestion box and I will reply on it. So thanks again.